All right, I'll begin today's session. So previous session we were discussing single phase half wave controlled converter wherein one SCR was used to rectify the input AC to DC. We obtained variable DC voltage across the load terminals by varying the firing angle. We had considered a RL load because of which there was stored energy in the inductor which caused the conduction to go beyond, or the current through the load to go beyond omega t equal to pi, or even after the supply voltage has reversed its polarity, there was some current which was caused due to the electrical inertia or stored energy in the inductance. As a result, conduction stopped only at an angle of beta, where beta was termed as the extinction angle. Alpha, you know very well, is called as the firing angle or delay angle. These were the concepts that we had discussed in the previous session. This session, we will discuss single phase half controlled bridge rectifier or a semi converter. Now, the configuration of a half controlled converter can be seen in two ways, can be viewed in two ways. One way is the SCRs being connected in the same leg, whereas the diodes connected in the other leg. So that is one way of viewing the circuit. This is called as leg. The vertical section is called as leg, and the horizontal thing is called as section. So you will have SCRs put up in one leg, diodes put up in another leg. This is called as asymmetrical configuration. Whereas you can have the SCRs in one section, diodes in another section. This is called as symmetrical configuration. But both configurations, they work in the same way. Meaning the output voltage waveform, V0 or any other parameter, supply side parameter or the current through the SCR, anything, nothing is going to change. All the circuit parameters will be exactly similar for asymmetrical and symmetrical configuration. Fine. And then the reason I'll keep stressing this, because you need to understand the basic difference. Don't get confused between half wave and half controlled. This is half controlled. There are 4 devices. Among those 4, out of those 4 devices, 2 devices are SCRs or controllable devices. Therefore, it is half controlled or semi converter. Whereas half wave will have only one device. All right, it could be a diode. It is called as uncontrolled half wave rectifier. If it is an SCR, it is called as half wave controlled rectifier. Only one device, half wave, for single phase. Whereas there are 4 devices, 2 SCRs and 2 diodes form a bridge. That is called as half controlled. So please be aware of the differences. Now let us look into the operating principle. As always, we assume an input sinusoidal voltage of Vs equal to Vm sin omega t, which is plotted over here. This is the input voltage. And this input voltage will be applied across the bridge. Now, from omega t equal to 0 to pi, the supply is positive. Therefore, SCR T1 will be forward biased. However, unless and until it receives a gate pulse, T1 will not conduct. Therefore, SCR is going to remain in forward blocking state. That state continues from omega t equal to 0 till omega t equal to alpha. Alpha is the instant at which gate pulse is applied to the SCR T1. The moment SCR T1 receives a gate pulse, it starts conducting. Therefore, current starts flowing from positive of Vs through T1, and then it flows through the load. Top terminal of the load will now be connected to positive of source. Therefore, top terminal will be positive. Current continues to flow through the load. Bottom terminal will be connected to the negative through diode D1. Therefore, load voltage will be exactly same as the source voltage, and we will be plotting load voltage from top to bottom. If you name the top terminal as A and B, then VAB will be V0. Quite obviously, A is connected to positive of Vs, B is connected to negative of Vs. Therefore, V0 will simply be following the input voltage. So if we plot the load voltage, it looks like this. Again, recollect, the instant at which SCR T1 starts conducting is called as firing angle. Magnitude of output voltage at that instant will be same as the input voltage magnitude. It shouldn't start from 0. If you draw a waveform starting from 0, you are wrong. It should start from a finite magnitude. It will not be 0. That finite magnitude is determined from the supply voltage. You simply put alpha equal to, let's say, if alpha is 30 degrees, put alpha equal to 30 degrees and V equal to Vm sin omega t. It will be Vm by 2. If it's 45, it will be Vm by root 2. If it's 90 degrees, it will be Vm. That's all. So the instant of firing, firing instant or firing angle determines this magnitude. These are important concepts. All right. Now, at omega t equal to pi, the supply voltage has reversed. Supply voltage has come down to 0. At that instant, Vs will be equal to 0. But there is stored energy in the inductor. This inductor will keep circulating the current. However, just after omega t equal to pi, Vs has reversed, which means the top terminal will be minus, bottom terminal will be plus, just after omega t equal to pi. That instant is shown over here. See, just after omega t equal to pi, this instant, somewhere here. If you want, I will use this pen as well. Now I am referring to this instant, somewhere here. I hope you can see, or I'll try to highlight as well. I'm referring to this point. Okay, just after omega t equal to pi, the supply voltage would have reversed. Now look into, or just observe the circuit. See, just after omega t equal to pi, because the supply reverses, diode D2 will be forward biased. Okay, or in other words, that is one way. Or the stored energy in the inductor will not allow the current to go down to 0. Therefore, it will force D2 to conduct. T1, it's not a problem at all because current through T1 should go down to 0. Only then T1 will be turned off. But that is not happening at omega t equal to pi or slightly after omega t equal to pi. The current through the inductance will force D2 to conduct and it will circulate through D1 load, etc. Because the load is short circuited, the voltage across the load will be 0. That is why you see the 0 voltage across the load. Right? This is what happens from omega t equal to pi till the next instant when T2 is triggered. Before that, T1 will keep continuing to conduct, assuming inductance is very, very large. All right. Are you able to understand these events from omega t equal to pi till the next instant, or how D2 is conducted? Now, from pi to pi plus alpha, that is the instant at which the SCR-T2 is triggered, because the load is freewheeling. This mode is called as freewheeling interval. I will comment it. This is freewheeling. Because the stored energy in the inductor is simply circulating among its terminals, within its terminals, through T1 and D2, T1 and D2. Therefore, it is called as freewheeling. This circuit, because you don't need any external device, it is called as self-freewheeling mode. The configuration is self-freewheeling in nature. Both symmetrical and asymmetrical, both are self-freewheeling. So this is what happens till pi plus alpha. At pi plus alpha, SCR-T2 will receive a gate pulse. Now you can observe this. See, already the supply has reversed. Therefore, the polarity of supply will be as marked over here. Therefore, plus positive of Vs will forward bias T2. Because it receives a gate pulse, it will conduct. And top terminal will be connected to again positive of the supply voltage. I will now name this as A and B for additional clarity. So B will be connected to the negative through D2. That's all. Now the current direction is going to be like this. It will start from positive of Vs and then it will flow through T2. Then it will flow through A and then terminal B. Then it will flow through diode D2 and then it closes. Fine. So this is the path for current. Now please understand these things. When you draw the circuit diagram, a jump over here is required, or put the supply here like we do in simulation. There should not be any joint or other things. If you have a node over here, then the circuit is wrong. You should not have a node, you should have a jump. Okay, that is why for clarity I have put both dot and a jump. You should not have a dot here. These things are silly things, they might look silly, but students keep doing such things. All right, so from pi to 2 pi, again T2 is going to conduct T2 and D2. They will be conducting, energy will be stored in the inductor. Again at omega t equal to 2 pi, the omega t equal to 2 pi, supply voltage reverses its polarity, but then current will not continue to, current will continue and it will not come down to 0. From 2 pi to 2 pi plus alpha, due to the energy stored in the inductance, it will force D1 to conduct. Thyristor T2 is already conducting, so current will circulate through T2 and D1. What is this mode named as?
Freewheeling.
Freewheeling interval. So this is again freewheeling. Therefore, magnitude of V0 will be equal to 0. That is what is shown over here. Then what happens after that? Cycle is going to repeat. Okay, at 2 pi plus alpha, SCR T1 will receive a gate pulse and then it will continue to conduct. At omega t equal to 3 pi, again conduction stops in one diode. It will be transferred to the other diode and there will be self-freewheeling. The cycle keeps repeating itself. This is what happens in a semi-converter or a half-controlled rectifier. Now, are you able to see any negative portion of the waveform in a semi-converter? Are you seeing any negative portion in the load voltage? No. Why? Why is that negative portion not occurring? Whereas in a half wave, it was there. Small negative portion was there. Load voltage was becoming negative when supply reversed. There was RL load. Here also we have RL load, but we are not seeing that negative portion. Why? Voltage is being short circuited. Whereas in half wave, what happened? Only one SCR was present. There was no freewheeling action. So this is the importance of the power diode. All right. You will not see the negative portion in the load voltage waveform. Even previous waveform, it was there. So this negative portion, negative small dip in the supply reverses, that will be cut off by this freewheeling diode. Both D1 and D2 self-freewheeling in action. So this is the output voltage waveform. Now, can you find out what will be the average output voltage waveform? Can you find an expression for that? Expression for average output voltage. Expression for V0 average. How do you find that? As usual, classical integration. 1 by 2 pi integral 0 to 2 pi V0 of omega t d of omega t. This is the integration that you need to perform. So from omega t equal to 0 till 2 pi, you need to integrate. You have two waveforms which are symmetrical, so I can simply put integral 0 to pi 2 times. And whatever you get from 0 to pi, or rather alpha to pi, or 0 to alpha, it will be 0, and then 0 to pi V0 of omega t d of omega t. Now you can find that you will get these two, this will get cancelled. 1 by pi integral alpha to pi Vm sin omega t, that's all, d of omega t. Okay, so if you now try to find out the expression, you will get Vm by pi into 1 plus cos alpha as the expression for average output voltage. Again, how do we vary? By adjusting the firing angle, we will be able to get, by adjusting this firing angle, we will be able to get V naught average, variable V naught average. One point. Another point, if alpha is more than 90 degrees, what will be the polarity of output voltage? It will still be positive. That is quite obvious because we don't get any negative voltages here. Therefore, V naught average will always be positive, even when alpha is more than 90 degrees. Whereas if you look into fully controlled converter, which will be handled after Cat1, the expression will obviously tell that when alpha is more than 90 degrees, you will get negative voltage. That we will discuss later. But for the time being, this is how we derive the expression for average output voltage. Oh, fine. So it is here. Performance parameters are the actual terms that are being used. The term that is used to quantify how the converter works. One parameter is V naught average. That, of course, I have derived the expression. It is put up over here also for clarity. Other interesting thing is supply side power factor. This is obtained using Fourier series and its basic principle. We will take up a simple numerical example and then we will try to solve. Fine. So this is one, the first numerical example. This is taken from this textbook, MD Singh. I have mentioned that. So this is what I'm referring to. You can refer to that textbook as well. Now, page number also I have given for additional clarity. A single phase half wave controlled converter is operated from 120 volt 50 hertz. So you now have VS, small VS rather. Supply voltage is given as 120 sine 120 will be RMS. Okay. 1 minute. I'll read and then whatever is required, I'll write. Let me not be in a hurry. 120 volt 50 hertz is the supply voltage. Load resistance RL is given. R is given as 10 ohm. RL meaning R suffix L, load resistance. Average, if the average output voltage V naught average is limited to 25% of maximum possible, which is 0.25 times V naught max. Maximum possible average output voltage. Determine alpha, determine, and this is what I was referring to, RMS and average output currents. I naught average, I naught RMS. Third point, third parameter that is required is again I naught is it's not I naught SCR, I average SCR, I RMS of SCR. These are the parameters that are asked, that are required. Now we will try to solve them. Okay. Now, what is the expression for average output voltage for a half wave controlled converter supplying R load? R load would mean conduction will stop at alpha. So if you do that integration, you will get V naught average as Vm by 2 pi into 1 plus cos alpha. You can actually try doing this for R load. V naught will be from alpha to pi only. Okay, so from the waveform, you can actually derive the expression for V naught average. Now we are given that its maximum value is 0.25 into V naught max. V naught max will occur at alpha equal to 0. V naught max occurs at alpha equal to 0. Therefore, 0.25 into V naught max equal to Vm by 2 pi into 1 plus 1. Cos 0 is 1, 0 degrees. So from this you can find out Huh? One moment. I think I have skipped 2 steps. Thinking too far ahead is not a good thing to do. Okay, 1 minute. I have skipped 2 steps, therefore. Now it occurs at alpha equal to 0 degrees. So the maximum value of V naught average that is possible, that is going to be Vm by pi. Therefore, V naught max equal to Vm by 2 pi into 1 plus 1. So 2 will get cancelled. So this would give me V naught max as Vm by pi. Okay, so this also can be found out as 2 in rather root 2 into Vrms, which is 120 divided by pi. So this value can be found out. This will be equal to Vm by 2 pi, which is again root 2 into 120 divided by 2 pi into 1 plus cos alpha. Okay, so from this you can find out alpha. To 70. Hmm. 25%, where is it? This one. Here it should be 25% into 0.25. So this is the maximum possible value. This I will erase. Probably here I will write. Maybe in another color to indicate the maximum possible value. Space. .25 into the rest of the things. Okay, so when you do that, 1/4 of this value, 1/4 of this value should be equal to 1/4 of this should be equal to Vm by 2 pi into 1 plus cos alpha. From that you just find out. Or in simple terms, 0.25 into this equal to the expression. So from here you find out what is alpha. Now did somebody find out? The firing angle works out to 60 degrees. Is that correct? I'm trusting the textbook, whatever is given here. Now second subdivision, it is about the RMS and average output current. Now I naught average is given by V naught average by R because it is a pure resistive load. I naught will be in phase with V naught, therefore I naught average will be V naught average by R. V naught average, you know that it is 1/4 of V naught max. So whatever you have computed, I think it's 40.4. Am I right? Should we compute again? Root 2 into 120 divided by pi divided by 4. Average will be this value by 10. That's all. This is 1.5 ampere. 1.35. Sorry, 1.35 ampere. Subdivision 1. V naught max equal to root 2 into 120 by pi. (120° is the correct value. Is that clear now? So I naught average will be V naught average by R, which is 1.35 amperes. Now, if you want to find out the RMS value, you have to find out from the waveform. So RMS value will be V naught RMS divided by R. Now V naught RMS has to be obtained from an expression. For V naught RMS should be obtained from the waveform. I think you know how to do that. You square it, root mean square. First square, take the mean, then take the root. First square, take the mean, then take the square root. So if you find an expression for that, you will get V naught RMS, the expression alone as this expression you can trust. The textbook will be given by Vm into, for whatever waveform we get for a half wave, please remember that, divided by 4 pi plus sine 2 alpha by 8 pi. Everything taken under square root. Right? So it is root of this entire thing is under square root. And you substitute alpha equal to 120°. Please be very careful when you do this, when you evaluate this. See, pi, if you take it as 3.14, express alpha as pi by 3. I hope the dimension both must be in radian. Okay, pi, if you put it as 3.14, put alpha as pi by 3. Else it will be horribly wrong, because I think you will now understand. Pi being 3.14, alpha being 120°, you are bound to go wrong. Minus 120 plus 3 will be minus 117 by 4 pi. It will be horrible. Please be very careful when you evaluate this. And don't trust the answer given in the textbook. That's why I'm not writing, because the expression alpha, everything is, expression alone is correct. Value of alpha is incorrect. Therefore, value of I naught average is incorrect. Value of I naught RMS is also bound to be incorrect. So you do and be ready with the answer. That's all. Please understand how to do that is enough. And SCR current, it is same as the load current there, because in a half wave, current through the SCR, current through the load, they are same. In a half wave controlled converter. Half wave meaning only one SCR. So in a half wave controlled converter, SCR current and load current, they are same. So whatever answer you get, same thing is true for the SCR current as well. That is with regards to half wave. Next example on semi-converter, whatever we had done today, whatever we had discussed today, same set of questions. Only difference would be in maximum possible average output voltage. Somebody was also saying Vm by pi into 1 plus cos alpha. That will be the expression for V naught. So V naught max will be Vm by pi into 1 plus 1, which is 2 Vm by pi. 25% of that should be equal to Vm by pi into 1 plus cos alpha. Find out what is alpha, and then you proceed further. For clarity, I have given this page number also. You can refer to that. On that note, I will stop.